Okay, so this is the last of the videos. I'll be going over 31 through 41 on the outline. We already talked a little bit about stoichiometry. It's going to come back up when we talk about limiting reactants and excess reactants, and again in how to make solutions and molarity and all that kind of stuff. So stoichiometry is going to be everywhere. So again, this is mostly going to be working problems. You will not be responsible for Beer's law. So even though that's on this review and there's an example of it, that will not be part of your test. It will be crossed out for you. So we're going to go back and we're going to work some limiting reactants. We are on question number 19 here. So here we're given a chemical reaction. So make sure when you see any chemical reaction that it is balanced before you start. If you see coefficients, it's probably been balanced. If you don't see any, then you need to check carefully. So this one, the Cu's are balanced, but the O's are not. We have a single O and two O's, so we're going to have to put a 2 in front of that one, which messes up our Cu's, which we can go fix. And then our carbons are fine. Okay, so A says 57.4 grams of copper 2 oxide is reacted with excess carbon. What mass of copper can be produced? So this is just straight stoichiometry. When it says excess, it means we don't have to care about how much carbon. There was plenty. So we're going to do 57.4 grams of CuO. Of course, the first thing we're always going to do is convert this guy to moles, so we need the molar mass. So we have copper plus oxygen. So we get 79.55 grams of CuO in 1 mole. Okay, but this one we're going to convert to mass of copper. So we're right here, and we're trying to get over here, and so this is a mole to mole ratio, which we're going to convert. So we use the coefficients. So 2 moles of CuO, 2 moles of Cu. Alright, so then this is a pretty easy calculation. And I shouldn't put it equal. It asks us to go back to mass. So we have to keep going. And 1 mole of copper, 63.55 grams. And then we can calculate. Alright, we're going to do sig figs with the number given in the problem. So 45.9 grams of copper. And that's our answer. So B says, we got the same reaction, but now I'm giving you 28.2 grams of carbon is reacted with 197.6 grams of copper 2 oxide, I'm sorry. So this time is different from A because in A I said excess carbon and now I'm giving you an amount of carbon. So the question said, can you determine the limiting reactant? So I am not sure how you were taught to do this. There's a possibility that you were taught to take both of these to a single product, which is absolutely fine and works just fine. You have 2 different calculations. Mine, the way I do it is I choose one of the 2 reactants and I convert it to the units of the other one. So I'm just going to choose this guy. So it has been chosen. It's arbitrary which one you choose. And then I'm going to convert it to the units of the other one. So I'm not using the other number. I've chosen the 28.2. I'm going to choose 28.2 grams of carbon, and my job is to convert it to grams of CuO. So I'm going to convert to moles first. Okay, then I have to switch chemicals, so I'm going to use my mole to mole ratio. So 1 mole of carbon is 2 moles of CuO using my coefficients. And then I'm going to keep going, and I have to go to grams of CuO. So I'm going to say 1 mole of CuO weighs 79.55 up in A. There's my molar mass. Alright, so units cancel except for grams of CuO. So I've got 28.2 divided by 1. Okay, so I get 374 grams of CuO. Okay, what this would mean is how much CuO you would need if you were going to use all 28.2 grams of carbon. So here's where I go, okay, well, now I compare it to that other number that I didn't use. I need 374 grams. I only have 197.6. So I do not have enough CuO. So CuO is limiting. Okay, so I know that you may have been given where you take both the carbon number and the copper 2 oxide and convert them to a single product, and then compare which one is lower. Either one should give you that copper 2 oxide is the limiting reactant. Just to show you that this method will work regardless of the number that you pick and how to interpret that. Okay, I'm going to move this over for just a second. So suppose you had chosen to start with the 197.6 grams of CuO instead of the carbon. So then if you had chosen this number, you would be converting 2 grams of carbon. So we would convert to moles, so 79.55 grams of CuO. Okay, then we would convert moles to moles, so we had 2 moles of CuO is 1 mole of C, and 1 mole of C is 12.01 grams. So if I go ahead and do that, I would get 14.92 grams of carbon, and that would be how much carbon that I would need if I was going to use all 197 grams of copper 2 oxide. So now is when I would compare it to that other number. Look over here, say, okay, if I need 14.92 and I was given 28.2, do I have enough? Yes, I do. That would be excess. And so still my limiting would be the CuO. Okay, so it doesn't matter. If you want to use the other method that you learned, that's absolutely fine. The only reason I use this method is that occasionally it saves me a little bit of work if I get lucky, if I'm asked a question like C. So C says, determine what mass of the excess reactant remains in the reaction in 19B. So the first way I worked it would not have saved me any work, but the second way I worked it, if I had chosen the 197.6 grams first, then I would save myself some steps. So it says, what mass of the excess reactant remains? So the excess reactant was carbon. So once to know how much is left over, we're going to have to do a subtraction. So I know I started out with 28.2 grams of carbon, and what I learned in this second time I worked this question, is that I would have used or needed 14.92 grams of the carbon, and so then I would have the difference left over. So I'm going to go ahead and do sig figs and get 13.3 grams of carbon left over. So if I had done my original choice where I chose to start with 28.2, it wouldn't have saved me any steps. I still would have had to do the second calculation. But either way, to answer C, you would have had to do that calculation. Just sometimes you can kill 2 birds with 1 stone. If you accidentally pick the right one first, you can answer both questions with that single line. Okay, so question 20 says, if 72.4 grams of copper is produced from the reaction in 19B, determine the percent yield of copper. So you should have learned that percent yield is actual over theoretical times 100, as all percents are. So actual comes from the lab, and theoretical comes from the math. So I'm going to say it comes from the line that we do. Okay, so everything we've been doing so far in this review is all theory. We haven't actually gone anywhere and found anything. So you should know that when you go to lab, it doesn't always work out perfectly how the math says. Things happen, things spill, air current blows things around. So there's always some error in there. So for the purposes of this problem, you're not going to the lab to work this review or the test, so I'm going to have to give you the lab number. Okay, so this is what this is. It's the 72.4 grams of copper is actually produced in 19B. So that's the actual. So for our percent yield, we're going to put 72.4 grams of copper on the top. So the other thing is, to find the percent yield is you're supposed to go find the theoretical. How much copper were you supposed to make theoretically by using a calculation? Okay, and so to do that, you always have to use the limiting reactant. So from 19b, we said that copper 1 oxide was the limiting reactant. So I'm going to use that guy's number. And so if you had done limiting reactants the other way, you may already have this. If you had happened to choose to go to copper, you may already have the amount of copper. I did not, so I'm going to have to calculate this. So I'm going to use the line to go find me still grams of copper. Okay, so grams 1 mole of CuO. Alright, then I'm going to say 2 moles of CuO. It's 2 moles of Cu. And 1 mole of Cu is 63.55. Should look just like what we did in A, it's just starting with a different number. Okay, so we should get 157.9 grams of copper. So that's how much you were supposed to make, and it says, hey, we actually made 72.4 grams of it. So we didn't do that great. So how you calculate the percent yield is you put the theoretical down on the bottom, and you multiply this by 100. Okay, so that guy goes right there on the bottom. So 72.4 divided by 157.9 times 100, and you get 45.9%, which is not great. Less than half of what you're supposed to get, but sometimes that happens. Okay, so 19 and 20 covered all kinds of stoichiometry and limiting reactants and percent yield. Okay, you may need some more practice on that, and there's some more on your take-home review. So 21 switches to Unit 4, but still dealing with this math and stoichiometry. Just switching to molarity, which we've already used at least once in these calculations. But A says determine the molarity of a solution. So molarity, you have to remember, is moles divided by liters. And so we've got 71.4 grams of KNO3. Okay, so we have to get that guy to moles. So we're going to look up the molar mass, calculate it. And we've got 101.11, 1 mole of KNO3. Okay, and you don't want to cancel out moles because molarity has moles on top. The only thing you need to do is put liters on bottom. So some of you may have to calculate that separately. Some of you may be able to look at 500 milliliters and convert it to liters, but it has to be liters. So this is 0.5 liters, which we're going to put on the bottom. If you are not able to calculate that in your head, little conversion from milliliters to liters, you have the milli conversion on the front of your equation sheet. Milli is the thousandths, so you'd get 0.5 that way. So this line looks a little weird to us here, because grams cancels, but moles and liters do not, and they're not supposed to. You're supposed to end up with moles on top and liters on bottom. So that's the only work you have to do for this guy. Okay, and the molarity comes out as 1.41 to correct sig figs. And you may either write moles over liters, or you can use the big M for molarity. Okay, B is still dealing with molarity, but solving a little bit differently. And instead of you being given grams and asked for molarity, I'm giving you molarity and volume and asking for grams. So the ways you guys set it up is you took your liters or milliliters, and so I'm going to convert it in the line so you can see that this time. So we've got liters here, or you can go to 0.765 if you can get there. And then you have to remember what this means. This is 0.20 moles over liters. That's what that is. So it's got 2 units hiding in it. So we want the liters to cancel out, so we're going to put the liters part on bottom, which means we're going to put the mole part on top. So that gives us our moles. And that is moles of calcium hydroxide. That was the molarity. And so the question says, can you determine the mass? So we're going to keep going, and we're going to convert moles to grams for about the 400th time. Alright, so calcium hydroxide has a molar mass of 79.10 grams per mole. And then we can calculate this, because now we have grams. Alright, so I calculate this and I get 11 grams. Okay, and I did 2 sig figs because the 0.20 has 2 sig figs. So there's my mass of calcium hydroxide. Okay, so that's basic stoichiometry with molarity, being able to use that big M and solve for the big M. 22 is talking about dilution, so you should have learned a formula for dilutions. Either this or this, or I think I've seen it where you use C1V1 equals C2V2. So C standing for concentration, that's absolutely fine. Just we're going to put in molarities as our unit for concentration. So any one of those is fine. If you look at that formula, you have 4 variables. They're going to have to give you 3 out of the 4 if they're going to ask you to solve for it. So we're doing a dilution. We've got 2 big M's. We've got 2 concentrations. And we've got 1 volume. So it doesn't really matter what you label these, C's, D's, 1's, 2's, whatever. The thing that matters when you calculate it for the math is that you pair the volume and the molarity that go together. So you got to pay attention to the English here, that 250 milliliters is of the 0.6 molar. So these guys have to be paired together. Now technically this guy right here is the diluted one. It has the lower molarity. And this guy is the concentrated one. It has the higher molarity. That's all that is. Okay. So doesn't matter what you call them, 1's or 2's, C's for concentrated, D's for dilute, doesn't matter. But we have 18 molar. We do not know the volume of this guy. We know the other concentration is 0.60 molar. And then as of this point, whenever we use molarity, we had to convert that to liters. But I want to show you something that works here. Okay, if you leave it in as 250 milliliters, when you go to solve this algebraically, you're solving for this V1. You're going to end up dividing both sides by this 18 molar. Okay, and what happens then on this side is the molarities cancel out. That's the thing that's dictating that it's liters, is the molarity. If the molarities go away, it doesn't matter what units you use for the volume as long as they are consistent. So if you do this, you can do 0.6 times 250 divided by 18, and this will tell you that V1 is 8.3, but the units would be milliliters. If you redid this and you decided that you were going to go to liters, okay, so you would have 0.60 and then 0.25 liters. Okay, the answer that would come out for V1 is 0.0083, but its units would be liters. These are the exact same answer, they're just in a different set of units, so it's up to you. Now you can't do this when you just have 1 molarity. You had to be in liters when we were doing a question like 21, but because there are 2 molarities here and they cancel out, you're allowed to use the milliliters or the liters interchangeably. You just have to make sure that both sides will end up having the same unit. So if you choose milliliters, the other side has to be in milliliters. Okay. So 23 is net ionics, was what we did on Tuesday in class. So remember, I'm going to cheat for you a little bit on these, and I'm going to give you whether the things are aqueous or not, and I can already tell that I failed on one of them. This guy right here is aqueous. I left that off, but I promise I won on the test. So if it says AQ, you're going to rip it apart, and if it says anything other than AQ, you are not to touch it. You are to leave it alone. But you do have to make sure that these equations are balanced before you start. So if you see any coefficients, trust me. If you don't see any coefficients, you should go check. And so I don't see any coefficients in A and B, so I'm a little bit mean here. You got to balance. So on polyatomic ions, I would treat the ClO4s as one big blob. Okay, so I would probably balance my O's and H's last because they appear in too many places, but we can see right now that the ClO4s don't balance. We're going to need a 2 over here to make our ClO4s balance. Our Mg's balance right now. Now I can look at my H's and my O's. So on the left side I've got 2 H's here, and I've got 2 more H's here for 4 H's. So I'm going to need to put a 2 right there to balance my H's and give that 4. And then on my O's, I am not looking at the O's in ClO4. I have already balanced those. So I'm just looking at the O's that are in hydroxide and then in water. And those balance now because we have 2 on each side. Okay, and you can go fully and balance them, and check everything individually, but it'll work here if you keep a polyatomic ion together. So now it's balanced. So now we rip apart anything that is AQ, and remember, a coefficient goes with both things involved. Okay. So the other thing is, if it's a subscript for only one of them, like over here, that's only going to go with the OH. Then remember that the positive always comes first. So when we rip this apart, it's going to rip apart into H plus and ClO4 negative. Okay, but because that 2 is out front, the 2 is going to go with both of them. The MgOH2, it says, is a solid. Leave it alone. It's less work for you. Okay, water, it says, is a liquid. Leave it alone. We're not going to rip it apart. And then MgClO4 says is AQ. We're going to break it apart. So the Mg has a 2 plus charge. We can tell that from the periodic table. We can also see it on the subscript down here for perchlorate. And then where the ClO4 is going to be ClO4 negative, but because it had that 2 subscript, we're going to put 2 out front there. And then we look at what we made, and anything that's identical on both sides we cross out, which is only the ClO4. Nothing else matches exactly. So we copy down what we've got left. And this will be our net ionic. And our spectator ion is just ClO4 negative, what was left. Okay, so on B, same thing. Remember I told you that BaNO3 was AQ. That was my bad. We need to make sure it's balanced. So I'm going to treat polyatomic ions as a blob. So we've got NH4s on both sides. I see NO3s on both sides. And I see SO4s on both sides. So I'm going to treat those all as big blobs. If I balance my yellows, I've got 2 on the left and 1 on the right, so I'm going to balance that. If I balance my SO4s, my blues, they look good, 1 on each side. If I balance my BAs, they look good, 1 on each side. And then NO3s, I've got 2 on the left side, and now I have 2 on the right side, so we're good. So now I'm going to go to ripping everything apart. So I've got NH4 plus and SO4 negative on the left side. But because of this little 2 subscript, I'm going to have to give 2 NH4 pluses. Okay, then I've got Ba2 plus and NO3 negative with barium nitrate. But this little 2 says I've got to have 2 nitrates. Okay, and then I hit my yield. Solid BaSO4, I do not touch. Okay, and then ammonium nitrate, it's AQ. I'm going to split it up so I get NH4 plus and NO3 negative. Okay, that 2 out front goes to both of them. Alright, so now I've got my total ionic. So I'm looking at anything that's identical. I see NH4 pluses. I see NO3 negatives. That's all that's identical, so I'm going to copy down what's left. And my spectator ions are NH4 plus and NO3 negative. Okay, make sure that you don't forget these guys. They're very important to show. Okay, and over on the spectator ions, it has to match exactly. Okay, so then Beer's law is what 25 is. You do not have to worry about this. You skipped this, so don't worry about that. It will be crossed out like that on your test. Okay, so the last one's a big one. The last one is going to be written like an essay question, but it's really just a multiple part for response. You're going to have to calculate, you're going to have to write. Okay, so it's actually talking about making real things, so you're going to be making solutions. So as I write these things to describe, I want you to think about how you would make a solution of lemonade or anything like that, because the process you physically use for making a bottle of lemonade or cup or pitcher of lemonade is the same thing you use to make any kind of solution. It's just we're going to make it worse because you're going to have to calculate. With molarities and grams and all that kind of stuff. Okay, so it says use the following reaction to answer the questions below. So A through D all have to do with this reaction. So first thing you got to do is you got to make sure this thing is balanced, and I don't see any coefficients, so I'm going to check. I can see right away the K's are not, so I'm going to balance those. Then I've got C's on both sides. I've got 1 on both sides. I'm good. O's, I've got 3 on the left side, and I've got 1, 2, 3 on the right side. H's, I have 1 on the left side and 2 on the right side, so I'm going to put a 2 right there. And that makes me have 2 Cl's on the left and 2 Cl's on the right, so there's my balance. So first up, it says describe how to make 250 milliliters of a 0.55 molar K2CO3 solution and include any necessary calculations. Okay, so what we have to do is, if you're going to make a solution, you have to have something that you can physically measure. So when you're looking at what you're given a volume and a molarity. If you're going to make a solution, you can't measure a molarity and you can't measure a moles. You can measure grams and you can measure volume for sure. Okay, so the things that we want to calculate is we want to know how many grams of this that we're going to have to put in. Okay, so when you make lemonade, you're going to have to go like how many scoops or whatever. Someone's already measured that out for you or figured that out for you, but you're going to have to calculate this. So we're going to start with our 250 milliliters, and we're going to convert this guy to grams. So we got 1,000 milliliters, so 1 liter. And then we've got this molarity, which is 0.55 moles per liter. So that converts us to moles of K2CO3, but we can't physically measure that, so we're going to keep going. And 1 mole of K2CO3. We're going to have to find the molar mass. Which comes out, I believe, as 138.21 grams. Alright, so when you calculate this, it comes out to be 19 grams of K2CO3. Okay, and that's a calculation, that's great, but you have to describe how to make this. So I'm actually asking you to make 250 milliliters of something. So if you're going to make that, the first thing you got to do is you got to get the right size container. So first thing we're going to do is we're going to get a 250 milliliter container. Okay, and the next thing we're going to do is we're going to add 19 grams of the K2CO3. Okay, so I want you to imagine when we're making lemonade, you put the powder in the bottom of the empty container right now. Okay, so once we do that, the third step that we're going to do is we're going to fill it with water to the top. Okay, so I want you to think about when you make that, when you make a solution of lemonade, if I said go make a cup of lemonade, you don't put the water in first and then add the powder. You don't. You add the powder and then the water because your total volume has to be 250 milliliters. If you think about the cup and you fill it up all the way with water and then add the powder, you're going to end up overflowing it. So we put the powder in first so we know that that's in there, and then we add the water. We never measure the water. You go turn on the sink, you just fill it up until it reaches the top. Okay, and the last thing we do is we cap it and we mix it. Okay, or we stir it. Okay, but when we make solutions in lab, the things that we make them in generally have a really skinny neck, and you're not able to stir them so much, so we just cap them and shake them up. Okay, but that's how you physically make it. Okay, so B says what volume of 0.1 molar HCl is needed to react completely with the potassium carbonate from part A. So this is just a purely calculation, not writing a description. So it wants us to find volume, and we're given a molarity. So the amount of potassium carbonate from part A, you can start with the 19 grams, or you can start with the molarity and volume. Just on the 19, you probably don't want to round anything. So I'm going to keep it as 0.25. That was my 250 over 1,000. So I'm going to do that. That gives me moles of K2CO3. This asks about volume of 0.1 molar HCl. So my problem here is I've got moles of K2CO3 and I need HCl. So that's what this reaction up here is for. We're going to convert, and so I'm going to use the coefficients. 1 mole of K2CO3. 2 moles of HCl. And now that I'm in moles of HCl, I can use this molarity. So that 0.1 is really 0.1 moles per liter. So I'm going to put 0.1 moles per liter. And that's going to get us the volume. Okay, so 0.25 times 0.55 times 2 divided by 0.1. So you get 2.75 liters of the HCl. So if you had chosen to start with the 19 grams instead, you would have had to convert it to moles using the molar mass. Either way gets you to moles. So if you'd done 19 divided by the 138.21, and then done the 2 and the 0.1, you would have gotten the same thing. Okay. All right, so part C says describe how to make the volume of 0.1 molar HCl determined in part B from a 12 molar stock solution. So if you look at this guy, we're given 2 molarities. If we're going to make the 0.1 molar from a 12 molar, this is a dilution. We are watering it down. So this is where you guys have C1V1 equals C2V2. You just have to pair the right things together. So it said describe how to make the volume of 0.1 molar HCl determined in part B. So the volume we determined was 2.75. That's 2.75 liters of 0.1 molar. So those guys are going to go together. So 2.75 liters times 0.1 molar is equal to, and then the other side we're going to have 12 molar and V2, whatever it is. Okay, so if we solve, this guy is in liters, so my answer is going to be in liters. So V2 is 0.022. Wait, I've got one sig fig, so 0.02 liters. Okay, so this one on the describe how to make is a little bit tougher, but you were trying to make a 2.75 liters of 0.1 molar. So you don't have 0.1 molar, you have 12 molar stock, and you have to make this 2.75 liters. So the first thing you got to do is you got to get a 2.75 liter container. Okay. Then there is an issue here. Normally, if you look back at A, what we did is we added the stuff in first, and then we filled it with water to the top. And that's what we should do here. But because we're adding HCl, which is an acid, we learned back in our safety thing that you should add acid to water and not water to acid. So what we're going to have to do is we're going to have to add a small amount of water to the container. We're not going to measure it. It's just going to be a small amount of water to the container so that our safety works. Okay. All right. Then we're going to add the 0.02 liters of the 12 molar HCl to the container. Then we're going to fill it with water to the top. And lastly, we're going to cap and mix it up, shake it up. Okay, so that one had a little bit of safety issue. All right, D says what mass of potassium chloride would be produced in this reaction. So it's all the same question, so we can use any of the numbers we've used before, except for from part C, that's how we were making something that we needed. So from A or B, those guys went together. So you can either use the 19 grams of potassium carbonate, the 2.75 liters of the HCl, the 250 milliliters of the 0.55 molar K2CO3. So most of you guys are probably most comfortable with the grams. So I'm going to go there and just use this one, but you could use any of them that you wanted. So we'd convert it to moles. That's moles of K2CO3. Okay, and then we were trying to go to potassium chloride, so we'd look at our coefficients, and we'd say 1 mole of K2CO3 is 2 moles of KCl. And then 1 mole of KCl, since we're going to grams, is 74.55 grams. And we're going to do all the numbers given to you in the problem that we've used. We used 2 sig figs. So we're going to give 2 sig figs. So we get 20 grams of KCl. Okay? All right, and the last is what physical observation would you have that would indicate the reaction above is happening? So I need you something you can see, hear, smell, touch. Something like that. We're not going to taste any of it, but physical observation that something above is happening. And so if you look at the reaction above, you actually have to pay attention. Everyone's different. Every reaction is different here, so it's not the same answer all the time. So what would you physically see happening if you were going to watch this reaction? So this guy, we would start out something dissolved in water and another thing dissolved in water. So we'd have 2 solutions. We wouldn't necessarily be able to tell the difference. Okay, and then what we would make is another thing dissolved in water and water itself, which we're not going to see make, but this guy right here is something different. Okay? So something different, if it's a gas and you form it in any kind of solution, if you think about soda, if you have a gas in there, the gas will bubble up. So because you made a gas, you would see bubbles and they would escape. Okay? You don't see bubbles if you make a solid or AQ. You see bubbles if you make a gas. So if you had made a solid, you would have seen something solidify and clump up at the bottom like we talked about with saturation stuff. Okay? So that is it.